Welcome guys, and here as promised is the second part of the video on scientific notation, prefixes and orders of magnitude. We are going to look at a selection of questions from the workbook and go through them. Some of them I will solve fully, but I think I have a few questions where I will simply give you a hint and then I expect you to proceed and complete the tasks. Okay, so here we go. Let's begin. The first question that I've chosen is from page 5 and level C. We are looking at question number 1C. All right, this question simply says it is on orders of magnitude and you're asked to express the human heart rate in orders of magnitude. So what do we know about how many beats per minute does the human heart make? Well, this is supposed to be general knowledge, just in the same way that TikTok is general knowledge, okay? So how many beats per minute does the human heart actually make? And if you've done this, or if you know this, then you would know that this is about 72 beats per minute. And so we want to express 72 beats per minute in orders of magnitude. Now, like we said, if you check the eWorkbook, the description is there. If we're going to write this in orders of magnitude, it means that we want to write it as 10 to the power of some integer number, okay? So if we're going to do that, we need to find the log to base 10 of 72. I'm going to explain this briefly. So the order of magnitude means we want to write this as 72 as being equal to 10 to the power of some value n, where n is an integer. Now, to do that, we need to change to logarithmic notation. I've explained this before, that n is referred to as the index or the exponent of 10, and 10 is usually called a base, right? So n is the exponent of 10, but the same n is called the logarithm of the number 72. So when we are referring to the base 10, n is called the index or the power or the exponent. But when we are referring to 72, then n is referred to as the logarithm. So we can write n is the logarithm of 72 under base 10, like this, okay? So the first thing is express n as log of 72 to base of 10. So if you haven't done logarithms, you need not worry. We are not going to spend too much on this. Logarithms is a topic that will come later. So all we need to do is to go really to our calculator and work out the logarithm of 72 under base 10. So if you are using, if you have an iPhone, for example, there is log to base 10 here. So this calculator, the calculator on iPhone or on an Android will be a reverse syntax, which means you type the number first and then press the log, as opposed to the typical mathematics calculator in which you will press the log and then enter 72. So this is a reverse syntax. So if you're going to use this, then you have to press your 72 first and then press log, and it will give you the value of the logarithm, okay? If you're using the calculator TI and Spire, for instance, then you have to press the log and then type in your 72. Okay, so all we need to do to find the value of n that needs to be here is to find the log of 72. If you do that correctly, you should get 1.857. But we have said that if we are going to express this in orders of magnitude, this needs to be an integer, right? N has to be an integer. So that means we have to round our 1.857 to the nearest integer. And the best integer, the closest integer that comes there is going to be 2. I think 1.857 is closer to 2 than it is to 1, okay? And for that reason, we can conclude that 72 can be expressed as 10 to the power of 2 in orders of magnitude. So this is orders of magnitude, okay? 72 in orders of magnitude, 72 can be expressed as 10 to the power of 2. I hope you got that right. The next, on the same page, we will look at question number 2. Express in orders of magnitude each of the numbers in level B3. So that means you go to the previous page of the booklet, and B3, that is question number 3 on page 4, is asking you to express some standard numbers there in orders of magnitude, and I think the first one there is 0.0385. So we want to express this in orders of magnitude. Like we've said, the best thing you want to do first, you could enter this directly into the calculator, but because I want to prepare you for some type of calculation, I want us to do this. So first thing we want to do is to write that number in scientific notation. If we express that in scientific notation, what do we get? 0.0385. The decimal point is going to move between 3 and 8, so that is 2 decimal places, and this number is less than 1, so k is going to be -2, and so we can write this as 3.85 times 10 to the power of -2. Okay, now this is already in orders of magnitude, so we need to express 3.85 in orders of magnitude. So 3.85, if you enter that onto your calculator, all right, in other words, find the log. We want the log to base 10 of 3.85. If we find the log of that number by finding log to base 10 of 3.85, you should find that n is 0.5854, okay, which is approximately equal to 1. Please pause the video and ensure that you're getting the same figure. And therefore, we can write 3.85 as 10 to the power of 1. N is equal to 1. So approximately this becomes 10 to the power of 1. And so now we can write 10 power 1 times 10 power, this is 10 power 1, multiplied by 10 power -2, like this. So 0.0385 can be expressed as 10 power 1 multiplied by 10 to the power of -2. Okay, we are multiplying similar bases, base 10. So by laws of exponents, we add the exponents. So 1 plus -2 should be -1. And therefore, that number there is just, in orders of magnitude, is 10 to the power of -1. I hope this is clear. I think we did another one here. I think it is F on the same exercise. Number F is 6,580,000. We want to express this in orders of magnitude. First thing is to express it in scientific notation. So 6,580,000 becomes 6.58 multiplied by 10 power 6. The decimal point is here. It's going to move 6 places to that point. That's why this is 6. And because the number we are turning into scientific notation is greater than 10, this 6 is going to be positive. So we have 6.58, and of course the number lies between 1 and 10. So 6.58 multiplied by 10 to the power of 6. Next, we need to write this in orders of magnitude. So to express that in orders of magnitude, we need to take log to base 10 of 6.58 to give us the value of n. Okay, so 6.58 can be expressed as 10 to the power of n. If we take to find n, we take log to base 10 of 6.58. If we do that, please do it on your calculator, you should find n is approximately 0.8182, which is also, if we round off to the nearest integer, that is going to be equal to 1. And so 6.58 is approximately 10 to the power of 1 in orders of magnitude. So I can replace this with 10 to the power of 1. So therefore I'm going to say, and for that reason, 6,580,000 is equivalent to 10 to the power of 1, which is this one here, and then I will multiply by 10 to the power of 6, and that gives me 10 to the power of 7. And therefore, in orders of magnitude, 6,580,000 can be expressed as 10 to the power of 7. This stuff is very, very easy. Orders of magnitude are going to be an obvious thing, a must in physics. So if you are equally a student of physics, then this is going to help you a great deal. Okay, very common in paper 1 of the IB diploma physics question, the multiple choice questions. Okay, We move on. Now, we don't always have to go about calculating the log to base 10 of a number in order to find the approximate order of magnitude. We don't need to do the calculation all the time. We just need to remember something. There is a very simple hack that we can use to always determine values of numbers to orders of magnitude. And to do that, let's take a look at the following numbers. So we will use our calculator to find the orders of magnitude of some of the numbers between 1 and 10. So for example, we know that 1 is 10 to the power of 0, and if you look for log to base 10 of 2, you should find it is 0.301. Please try that out. So 2 can be expressed as 10 to the power of 0.301. Okay. Similarly, if you find the log to base 10 of 3, you should find that it is equal to 0.4771. Okay, and therefore 3 can be expressed as 10 to the power of 0.4771. It continues, of course. We only need those number of decimal places. If we look for 4, 4 is going to be 0.602, and 5 is going to be 10 to the power of 0.699. Okay, and so on. 8 is going to be 10 to the power of 0.901, and 9 will be there, and 10 is going to be, of course, 10 to the power of 1. So there's something I want you to notice when you look at these numbers here. First of all, let's just round these to the nearest integer so that we find these values in orders of magnitude. So if we round off 10 to the power of 0.3, 0.3 is less than 0.5, so it's closer to 0 than it is closer to 1, and therefore 10 to the power of 0.3 rounds off to 10 to the power of 0. It's closer to 0 than it is closer to 1. Okay. Similarly, 10 to the power of 0.477 is closer to 0 than it is closer to 1. It is below 0.5, so therefore it's closer to 0 than it is closer to 1. Okay, but 10 to the power of 0.6 is now closer to 1 than it is closer to 0, so this one rounds up to 10 to the power of 1. Similarly, 5 will round up to 10 to the power of 1. Okay, and 8 there, obviously 6, 7, and 8 is also 0.9, so clearly the power is increasing. So 8 is also going to be closer to 10 to the power of 1, and of course 10 is 10 to the power of 1. So if you look at this, okay, numbers which are less than 0.5 will round down to 10 to the power of 0, whereas numbers whose powers 10 to the power of, if the number here is greater than 0.5, it will round up to 10 to the power of 1. If you look here, you should be able to notice that. And this is very important. What is telling me that there has to be a number here lying between 3 and 4 whose log to base 10 must be 0.5, somewhere in there. So if we check somewhere right there in between, there is a number that lies between 3 and 4 whose log to base 10 is going to be 0.5. Which number is that? If we can find that number and remember it, then it becomes the magic number that we will use to hack the orders of magnitude. Okay? So to find this number, all you need to do is to type in 10 to the power of 0.5 in your calculator. That should not be very difficult. And when we do that, we will find that 10 to the power of 0.5 is in fact 3.162277, and it continues. We don't need to remember all of it. If we can remember 3.162, that will be good enough. So keeping that in mind, I can now arrange my numbers from 1 to 10 like this. Okay, so this the 3.162277 is actually the boundary. Okay, so there it is, I'm putting it there, which is to say that numbers that fall below, if I have a number that I want to convert to orders of magnitude, and it is below 3.162277, any number below that will always fall back to 10 to the power of 0. And any number that is above this, so 3.5, 3.3, 3.2 in fact, okay, will always round up to 10 to the power of 1. So this is the hack that we need to use to determine orders of magnitude. Here is an example of what I'm talking about. So now all we need to remember is 3.162 as our boundary. If a number falls below this number here, then we will express it in orders of magnitude as 10 to the power of 0. If a number is greater than 3.162277, then we will express it as 10 to the power of 1 in orders of magnitude, okay? Approximated to orders of magnitude. All right, here is an example. Express 2,480 times 0.580 in orders of magnitude. In order to answer this, the first thing we want to do, now we will not use a calculator at all, we will rely on this number here. But the first thing we have to do is to express these numbers in scientific notation. So 2,480 is going to be 2.48 times 10 to the power of 3, while this one is going to be 5.8 times 10 power negative 1. Please check and be sure you understand that those numbers have been expressed in scientific notation. Now all we have to do is look at this number and compare with our magic number there. So 2.48 is less than 3.14, and therefore because of that we will give it in orders of magnitude as 10 power 0. Okay, so that becomes 10 power 0. 2.48 in orders of magnitude approximately is 10 power 0, so we will put that there, 10 power 0. Then we'll multiply by our 10 power 3 as before. Okay, and now 5.8 is a number that is greater than 3.162, and therefore we can round it up, okay, in orders of magnitude to 10 to the power of 1. So I'm going to write this as 5.8 as approximately 10 to the power of 1 in orders of magnitude, and so I will put that there for 5.8, and then I'll multiply by my 10 power negative 1. Okay, now we have similar bases, base 10, and so by laws of exponent we add the exponent. So 0 plus 3 plus 1 is 4, minus 1 is 3, and therefore this product here rounded to the nearest order of magnitude is going to be 10 to the power of 3. As simple as that, okay? So anytime you need to write a number in orders of magnitude, please first express it in scientific notation and then compare the numbers lying between 1 and 10 with the magic number 3.162277 to determine the order of magnitude. It should be straightforward, really, okay? Hoping that was okay. Now we go to page 6. Level C, and now we're looking at question number 6. Okay, in this question I'm merely giving you hints on how to proceed. Okay, I would expect you to research some of these values. So there are certain values that are described but not given in numbers, so you probably wonder how much these values are, but if you go online and just check briefly, you should be able to find those values easily, okay? In any case, they are approximations, so there is no one specific value. All right, for example, the mass of a small car, well, nobody says which car because cars have got different masses, so anything lying between 600 kilograms and 1200 kilograms would be the mass of a small car, okay? So any number really, you can work with any of these numbers. So if you say 750, you would be fine, and you are being asked to express that in orders of magnitude. So if we were to take if the mass of a car was say 750, then we'll say 750 kilograms, and we want to express that in orders. We want to express this in orders of magnitude. So let's say the mass of a car is 700, I'll write it here, 720 kilograms. How do we express this number in orders of magnitude? Well, the first thing is to express this in scientific notation. It becomes 7.2 multiplied by 10 to the power of 2. And now the 7.2 is greater than 3 point, so 7 7.2 is clearly greater than 3.162277. You don't need to remember all of it. 3.16 is good enough. And therefore, 7.2 is approximately 10 to the power of 1 in orders of magnitude. And so I can write 720 as being equal to approximately 10 to the power of 1 times 10 to the power of 2. And so this is approximately 10 to the power of 3 when we add 1 and 2 there. So in orders of magnitude, the mass of a small car is 10 power 3 kilograms, like that. Okay? So any number really that you would choose lying between around 600, even 500, and 1,200 would be the mass of a small car. You should get the same value for the order of magnitude. Okay, next was C, the average mass of a full-grown man. In the eWorkbook, I think I wrote this as mass. That was a clerical error. So just note that we meant full-grown man. Okay, well, men are of different masses. There are those who are up to 200 kilograms, and yet there are others that could be as light as 50 kilograms. So the mass of a full-grown man ranges between 50 or even less to around 200, 300 kilogram people have been seen. So any of those values, just put it in and try to change that into orders of magnitude. You should get the same thing. I think that should be about 10 to the power of 2 if you do it correctly. So try it out and find out what the answer is there. A particle of sand has an average volume of 0.1 cubic millimeter. Okay, so with that information, you should be able to find the number of particles of sand in a container as described in the workbook. Okay, for on page 6, question number 4. Take a look and let me know what you think. Okay, find your answers and then let's compare them. I hope to see your questions in the comment section. All right, next. Page 6, level C, and now this is question number 5, okay? The distance from Sun, which is in Geneva, to Gran Sasso, which is in central north of Italy, is 732 kilometers, okay? So we are looking at northern Europe. Sun is somewhere there in Geneva in Switzerland, and what you see here is Italy, and that's where Gran Sasso is a scientific facility, a research facility. This is a high energy particle physics facility or a research station. So that distance is 732 kilometers. At Sun, they generate tiny fundamental particles called neutrinos, and they direct neutrinos underground to Gran Sasso. And this was a faulty experiment, if you read about this. And when they did this experiment, the experiment appeared to show that neutrinos travel faster than light. Light travels at about 2.99 times 10 power 8 meters per second, and this was showing that neutrinos are traveling faster. Of course, eventually they found that there were errors with the experiment, and so nothing, as far as we know, travels faster than light, okay? But assuming that we work with the calculations that they found, that 732 kilometers, neutrinos were traveling at that speed, the question you're being asked is to find the time it takes using this data. How long does it take for a neutrino, which is a fundamental particle? Neutrinos would be smaller than electrons, smaller than atoms, definitely smaller than protons and neutrons. So what time would it take a particle called neutrino to travel from Switzerland to Gran Sasso in Italy? To answer this question, we need to remember the relationship between time, distance, and speed. Time is equal to distance over speed. I hope we know this, but if you don't, well, now you know. So if the distance being covered is 732 kilometers, Okay, we probably need to change that into meters. So we change the distance in kilometers to meters. So we get 732,000 meters. Okay, because 1 kilometer is 1,000 meters, and the speed is in meters per second as indicated there. And when we divide this on your calculator, we should get 0.0024399 seconds. Please do this and check that it is the correct answer. And if we are to give this answer in scientific notation, then we have to write 2.4399 times 10 to the power of negative 3. But of course, this is to how many significant figures? So that is 7 significant figures. But this is to 3 significant figures. So because we are dividing, our answer needs to be to 3 significant figures. And so we would round that number to 2.44 times 10 to the power of negative 3 seconds. Also, you could write that as 2.44 milliseconds, okay? Because 10 to the power of negative 3 has got the prefix milli. So 2.44 milliseconds, or 2.44 times 10 to the power of negative 3 seconds, okay? Right, let's go to... Right, let's go to the next one. On page 7 and level D questions, we are looking at question number 2. The formula for the force keeping a satellite of mass m in orbit around the Earth is given by force is G times m over r plus h into bracket squared, where G, given by that value, is called the universal constant of gravitation. M would be the mass of the Earth, capital M. Small letter m would be the mass of the satellite. So the mass of the Earth is 5.98 times 10 to the power of 24. It's given in the question. The mass of the satellite is, I think, 11.3 kilograms. Okay. We are also told that the radius of the Earth is 6,374 kilometers. 6,374 kilometers is the radius of the Earth. And the height of the satellite above the Earth's surface is 35,786 kilometers. This kind of height is the height of a type of satellite called a geostationary or geosynchronous satellite, also called parking orbit. This is a satellite that stays above the Earth's surface on the same spot as the Earth is spinning. So here's an example of a geosynchronous satellite. Okay, so if, for example, we had a World Cup happening in Qatar, then the satellite would move to just above Qatar and stay on the same spot in order to transmit information from that region. Okay, so this would be referred to as a geosynchronous satellite. Otherwise, most satellites are usually lower than this height. Okay, so this is a height above the Earth's surface. So h is referring to the height above the Earth's surface of the satellite, and r is referring to the radius of the satellite itself. Okay, so we need to substitute this data into that equation. But before we do that, the distances must be in meters if the force that we are calculating is going to be in newtons. Okay, so here are those values again. But like I've said, if we're going to find the force in newtons, the unit of force is newtons. If you're going to find that in newtons, then these distances need to be in meters and not kilometers. Okay, the mass is in kilograms, which is fine, but the distances must be in meters. Okay, so to change the distance to meters, so this is r is going to be 6374 and 3 zeros. Like that, or 6.374 times 10 power 6 meters. I've expressed it now in scientific notation. And the height of the satellite above the Earth's surface is also going to be in scientific notation, expressed in meters, 3.5786 times 10 to the power of 7 meters. Okay, now this data need to be substituted into that formula there. So if we bring in our calculator, okay, substitute in this data, place this data in your calculator. Okay, so that is the value of G, that's the mass of the Earth, that's the mass of the satellite expressed in scientific notation, divided by radius of the Earth plus the height of the satellite. If we enter this data in your calculator, this is a TI Inspire, which is what my students would have. If you enter this data into the calculator, I suggest that you use, there is a tab here just next to the book. There is a book symbol somewhere here. So if you use that that button there, it gives you a fraction where it becomes easier to type in your data so that you do not make mistakes. Okay, if you enter that into your calculator, you should get the value of about 2.54 times 10 power 0. In other words, 2.54 newtons. That's like the weight of a lollipop, really. Okay, or your pen. So it becomes very light at that height. The satellite does not experience much pull of the Earth. The pull of the Earth becomes very, very small. Okay, so then that's the answer to question number 2 on page 7, level D tasks. Okay, let's move on. Question 3 on the same level D tasks, page 7 still, says the value of a property. So you buy a property like a home. The value of a property, A subscript T, after T years, so T refers to the time for which you've owned the property. So when you buy a property, usually properties like housing and so on, land, the value increases as time progresses. So we say that the value of the property appreciates. Okay, so you buy a property at some amount. A naught is the amount for which you buy the property. R refers to the rate at which the property appreciates every year. Okay. N refers to the how many times it appreciates or it is compounded every year. And T is the time when we want to check the value of the property. So we buy a property. This symbol here is for Swedish krona, which is the unit of currency in Sweden. So if you buy a property for 800,000 krona, which would be about 8 million Kenyan shillings in my country. So you buy a property for that amount and you leave it on for 10 years. Okay, it is compounded every year. All right, at a rate of, I think the rate is also given. So we leave it on we own it for 10 years. We're going to check how much it is worth after 10 years. The rate at which it appreciates is 0.9619 and N is equal to 1 because we are compounding or we are calculating the appreciation once every year. Okay, so we want to find out what the value of this property is going to be after 10 years. Okay, well, that rate is very, very small, so we do not expect much appreciation. But of course, in real life, this rate will usually increase also. It doesn't stay constant, and therefore in real life the appreciation can be much larger. But if we assume that the rate of appreciation remains constant, then let's see the calculations. All we need to do is to enter that data into that formula using your graphical display calculator. GDC means graphical display calculator, such as this one. You don't need a graphical display calculator, of course, but this makes life easier. TI-84 will do it as well. TI-83, Texas Instrument or Casio, doesn't matter. You should be able to do this easily. So if we enter this data, what we have, you should enter the amount after 10 years is going to be 800,000 into 1 plus R is that value there, 0.9619 over 100 multiplied by N, which is 1. And then everything into bracket, power 1 times the time for which we are going to check this, which is 10 years. So if you enter that into your calculator and solve it, we get a value of 880,369.80 krona. Okay, so there is an appreciation of about 80,369 krona, 370 krona. That is the the interest or the appreciation. Okay? If the answer is required in scientific notation, then it is 8.803698 multiplied by 10 to the power of 5. Okay, that is how we answer that question. Let's move on to the next one. This is on page 7, but now level E, question number 1B. Question number 1B says, how many meters, so now this is the use of prefixes, how many meters are there in 18.60 centimeters? So to answer this, we want to change from centimeters to meters. We will say the value we are looking for, let's call it x. So x meters must be equal to 18.60 centimeters. So this is how I suggest that you start answering the question. There is a value we are looking for, which is x, and it's measured in meters. So we'll say x meters is 18.60 centimeters. And then we remember from our table of prefixes that the centimeter there means the same thing as 10 to the power of -2, or 100th. Okay? So therefore, we are going to remove the c there and replace with 10 to the power of -2, and therefore our value of x is going to be 18.60, and then in place of c we drop in 10 to the power of -2, and the meter remains. That meter still remains here. So that's what we have. This is the same as dividing by 100, so it's 18.6 divided by 100, and if we do that, we should get 0.186 meters. So 0.186 meters is equivalent to 18.60 centimeters. There are 0.186 meters in 18.60 centimeters. Okay? All right, let's do another one. Question 1D, it says, how many kilobytes, and I think the spelling in the eWorkbook has an I here, it should be Y for bytes. Okay? So how many kilobytes are there in 1024 bytes? So this is slightly different, so we will say there are x kilobytes, same story, there are x kilobytes in 1024 bytes. We want to know how many kilobytes are these. Now all we need to remember is that the kilobyte there, okay, that k there implies 10 to the power of 3. It's the kilo, okay, which is equivalent to 1,000. So we can replace that by 10 to the power of 3, and so we will have x times 10 to the power of 3 there bytes is 1024. And then what we need to do is to divide both sides by 10 power 3 bytes. So divide by 10 power 3b, divide by 10 power 3b, and what you end up with is going to be 1.024. And because of that, we can now conclude that there are 1.024 kilobytes in 1024 bytes. Okay? There are 1.024 kilobytes in 1024 bytes, like that. Okay? So if the prefix is on this side, then you put it down and then you divide both sides by the same. Okay, like we've done here. All right, here's another one which should be similar to this. All right. Question 1E. It's asking how many gigaseconds are there in 5,600.4 megaseconds. Okay, how many gigaseconds? So once again, x gigaseconds must be 5600.4 megaseconds. So x gigaseconds is equal to 5600.4 megaseconds, like that. Then we have to remember what the giga means. If you remember this, you can pause the video and try to think about it. All right. Otherwise, the giga is equivalent to 10 to the power of 9. Okay. So we are going to replace that g there with 10 to the power of 9, like that. Okay. And now if we want to know the value of x, we have to divide both sides by 10 to the power of 9 seconds. 10 power 9s. If we divide both sides by 10 power 9, Okay, so this is going to be mega. So there is an m here because s will cancel with s if we divide both sides, but we will have m left there. If we work that out, we end up with, I've written the numerator in scientific notation, and that gives me 5.604004 times 10 to the power of -6. Okay, so there are 5.6004 times 10 power -6 gigaseconds in 5,600.4 megaseconds. I hope you're understanding the gist of solving problems of this nature. Okay? Then on page 11, level F, we are looking at question number 2. Okay, question number 2A asks, it's about Amanda has bought a housing plan and wants to construct a home in a given land area. The land is placed in a square grid, a millimeter square grid. Here is the piece of land. Okay, the question is to find the plan area. Part A was to find the plan area in square millimeters. So what is this area here in millimeters squared? And the hint is either you're going to count all the squares, which is not going to give you a very accurate answer. The better thing to do is to split the triangle, split this shape here, the whole area, into triangles and rectangles. You can do it your own way, but I have given an example of what you might do. So I've split it up like this. So that's one region, another region there, and I've made a rectangle somewhere central, right? Like that. And then I have named the different areas that are resulting, okay, D and E at the end there. So then you have to find the area of each of those triangles. There are 4 triangles there whose areas are to be found, and there is a rectangle at the center whose area can also be found. Now the length of one square is 1 millimeter. So if I count those number of squares all the way up to there, up to the end, I think I found 20 millimeters. And then I also counted the height, the distance from this point all the way up to there. I can't remember what I got, but let's just take a look. I have done the calculation. So the area of that triangle A, I have found that to be, so area of a triangle is given by that formula. Area of a rectangle is length times width. So if I use that to find the area of triangle A, so I found this length to be 20 and that height to be 14 millimeters. Please check it out. Try counting them yourself. You should find the base of this triangle here to be 20 millimeters, and the height from there all the way up to there, vertical height there, that should be 14 millimeters. So if we substitute that into the formula, I found the area to be 140 square millimeters. Okay, similarly, I found the area of B. I found the length here, and the width there. So what did I get? So for B, the length was 18, and the width, this width here, was 8 millimeters. So 18 times 8 is 144 millimeters squared. Okay, so that was the area of that region B. Okay, your job is to find the area of region C, area of region D, that triangle D, and of triangle E. And once you've done that, so you'll find those 3 areas and then add all those areas. If you've done this correctly, you should find the total area to be approximately 363 square millimeters. Please do it and ensure that you're getting the same thing, or discuss with me your value. Okay? Okay, so the total area is given in millimeters squared, is given by that. If somebody had asked us to find that area in square meters, then it should be 3.6 times 10 to the power -4. Nobody wants you to do that, but I've just put it there in case. All right, so that is the area of the plan area, the area on the piece of paper. Okay, but part 2 of the question says that there is a scale being used regarding what's on paper and what's on real land, right? That there is a scale for construction which is 1:25,000. Now on the eWorkbook I left 1 0 here. Please add that 0 there. It's not 2,500, it is 25,000. So 1:25,000 is the scale relating what is on paper and what is really on the ground. Okay, so find the actual area of that plot of land that Amanda is going to use for home development, right? So how do we go about this? So a scale of 1:25,000 means that 1 millimeter on the piece of paper will represent 25,000 millimeters on real land, okay? Which is the same as 25 meters in real land. Okay, so let's see. So this is just telling you that there was an error, 1 0 there was missing in the eWorkbook. Just ensure you put it there. It's not a big deal really. And so now the scale is 1 millimeter is 25,000, represents 25,000 millimeters. Every millimeter represents 25,000 millimeters, or 25 meters if you like. Okay, and so if we square both sides, then 1 millimeter squared must be this thing here squared, right? This value squared. So in reality, 1 square millimeter must represent 25,000 millimeters squared. So we have to square. If we square this side, then we have to square this side, and that gives me 625 million square millimeters. So every millimeter on paper represents 625 million millimeters on land. Okay, all right. Now but we found the area in millimeters in part A. 1 millimeter, we already know 1 millimeter represents 10 to the power of -6 meters. I hope you know how to change this. Please check the eWorkbook. We've talked about that. 1 millimeter is 10 to the power of -6. 1 millimeter squared is 10 power -6 meters squared. So with that information, then what about this number of millimeters squared? If 1 millimeter squared is 10 power -6 meters squared, how many meters squared is this value? So therefore, 625 million millimeters squared must be 625 million multiplied by 10 to the power of -6, okay? So what I've done here is I've just expressed 625 million in scientific notation, makes life easy, and then multiplied by 10 to the power of -6 for 1 millimeter. And if I work that out, you should be able to see that that is giving me 6.25 times 10 power 2 square meters, which is also the same as 625 meters squared. Okay, so the area of the piece of land where this lady is trying to build her home is going to be 625 meters squared. So the answer was required in meters squared. So you can leave it as 625 meters squared, or you can express it in scientific notation. Either way, this is the actual area on the ground that is going to be used to build the home. Okay, please let me know if this is not making sense, and we can discuss it further with you. Okay, place comments in the comment section, and that will solve a great deal of our issues, if any. Okay, let's see if there's another one. Question number 5 on page 12, and now we are on level F. Okay, so a Moscow sugar packet, that is a packet used to package sugar cubes, measures 16.2 centimeters by 9.6 by 5.5 centimeters. One sugar cube measures 16 millimeters by 15 millimeters by 8 millimeters. How many cubes can fit in the packet? All right, this is not bad. So the first thing, of course, is we want to know the capacity of the packet, or the volume of the container, which is the packet. And we also want to know the volume of each sugar cube. All right, so to do that, here is the Moscow sugar packet. So this is sugar as sold in Russia. Okay, so this measures 16.2 centimeters, that's the height there, by 9.6, which is the length, by 5.5, which is the breadth there. Okay, and we have sugar cubes inside. You can see those white, whatever represents the sugar cubes that are going to fit in there. All right, so how are we going to solve this? Like we've said, we find the volume of 1 cube of sugar in millimeters cubed. So we make use of this information for 1 cube. If we multiply those three, we will get the volume of a single cube in millimeters cubed. So that is going to be, if you do that calculation, you should get 1920 millimeters cubed. That's the volume of 1 cube of sugar. All right. The volume of the container, or the capacity of the packet, is found by multiplying those values. If we are going to compare the two, then they need to be in the same unit. So I have chosen to change these values to millimeters before multiplying them. To change from centimeters to millimeter, we just multiply by 10, because 1 centimeter is the same as 10 millimeters. So 16.2 centimeters is going to be 162 millimeters. Okay, 9.6 centimeters will be 96 millimeters. 5.5 centimeters will be 55 millimeters. So we need to multiply those three. We have 162 times 96 times 55. Those three values are all in millimeters, so the answer should be in millimeters cubed. If you use your calculator to find that, you get 855,360 millimeters cubed as the volume or the capacity of the container or of the packet. Okay, that red packet that we saw. Now, if we're going to find the number of cubes that fit in here, then that's the volume of 1 cube. So how many will fit in this? We have to take this value here and divide by that value. Hopefully that makes sense. The number of cubes, this means number of cubes, must be equal to volume of the packet divided by the volume of the cube. The volume of the packet is 855,360, and the volume of 1 cube is 1920 cubic millimeters. If we divide that on your calculator, we get that we will have, I think it was 445.5, and so I rounded that up to 446 cubes of sugar that will fit in the sugar packet. Okay, I believe that brings us to the end of this video. Hopefully you were able to follow closely, and that you found everything interesting. If there is any question that you're not able to answer or something that needs clarification, do not forget to send me comments in the comment section, or send me a message on Facebook. The Facebook link is also included in the comment section. Okay, I will include a copy of this ebook in the comment section as well. So in case you've lost your hard copy or anything like that, then you can still access it. All right. So then this brings us to the end. Please remember, if you have not subscribed yet to the channel, please remember to do so, and hit the notification bell so that when we bring in a new video, you will be notified. All right. Share the videos widely so that those that might find some help or that might need them can also find relief using the videos. Okay, thank you very much. I will see you in the next video, where we are moving on to eWorkbook number 4, which will be on number sets. Okay.